Class, in this lesson we're going to take a look at systems of equations, and to start we're just going to be determining if an ordered pair is a solution of a system. Our system is two linear equations that could be graphed and make a line, and the question is whether or not this coordinate works as a solution or is part of the solution set for this system. And the easiest way to do it is just plug in the 4 and the 2 in for x and y respectively. In other words, you want to see is 4 plus 2 equal to 6. And yes, that is, it checks out, so it works in the first equation, and then you try in the second one. It's 4 times 4, so 16. Well, let me write 4 times 4. 4 times 4 here, minus 2. Okay, so 4 times 4 is 16, minus 2, does that equal 14? Yes, it does, it checks out, so this ordered pair is a solution to the system. So let's try another one. I've got negative 1, 7, and this is my new system, so I plug it in. Put in my negative 1 right here, and I'm going to be timesing that by the 3, so it's going to be negative 3 plus 2 times 7, which is going to give me 14. So negative 3 plus 14 does give me 11, so that one checks out, but I don't get to say it's a solution just yet. I have to plug in the second one. When I plug in the second one, I get negative 1 minus 5 times 7. Okay, and 5 times 7 should give you negative 35, and then we get the negative 1 in front of there, which should add up, so it's negative 35 and negative 1, which should actually add to be negative 36, but that's not what we have here. This is a positive 36, so this one did not work, which means this is not a solution to the system. It may have been a solution to the first equation, but it's not a solution to the whole system. You have to plug it into both equations. Okay? So that's your first intro to systems. Now we actually are solving the systems to see where the answers are. There was a few methods, the first of which is graphing. To solve a system by graphing, we're supposed to think back to graphing a line. Basically, you got two lines here, line number 1, line number 2, and you're supposed to graph them both on the same grid. And in order to do that, we want to get y alone. So I'm going to get y alone in this first equation by subtracting x to the other side. And I'm going to get y equals negative x plus 5. And I put the x first again because I want it in y equals mx plus b, so that I know what my slope is. It's the m, and my b is the y-intercept. So I go ahead and put a dot on 5, okay? And from there I'm going to go down 1 over 1, and you keep going down 1 over 1 as many times as you want, and connect the dots, okay? So now, that's my first line, and it keeps going in both directions. Now I graph the second line by subtracting my 2x, and I'll get negative y equals negative 2x plus 4. And I have to finish by dividing everything by negative 1. Okay, if you divide everything by negative 1, it will cause all your signs to change so that you get y equals positive 2x minus 4. So now when I graph this one, I'll go down to negative 4, and from there I'll go up 2 over 1, up 2 over 1, and you can keep going up 2 over 1 forever, but we only care about that coordinate right there that I circled, and that coordinate is 3, 2. The coordinate 3, 2 is where the lines crossed. Solving the system is really trying to figure out that right there. Where do the lines cross? The coordinate 3, 2 is your one and only solution to this system. Okay, so the whole time we're going to be solving by different methods now, algebraically, but the whole goal is that each one of these systems represent two lines on a grid, and we're hoping that they cross. Okay. Now there's a few different things that can happen. First of all, let's erase this. So ignoring this problem that we have here, I can have two lines that are parallel. Now if I get parallel lines, I'll end up having no solutions. I might have lines that just cross at one place, and that'll give me one coordinate, just like this last problem did. Or I might have what we call coinciding lines, where the lines are right on top of each other and it's the same line twice. If that happens, we'll get infinite solutions. So there's a few things that can happen. We'll see that could happen graphically, like these, or what we're going to learn how to do is solving by elimination, algebraically. Okay, to solve by elimination, basically we want to think back, well, first of all, there's supposed to be a little bracket here. We want to think back to basically whenever we first learned vertical addition. If we draw a line right here, we want to do vertical addition. So we just add our columns. I want to add the 4x and the x's. I want to add the 2 and the negative 2, the 7 and 3. What I'm hoping happens is one of my variables eliminate. Okay, eliminate means cancel or to be gone. So when I add vertically, I'm going to get 5 x's and my y's eliminate. Okay, you want one of your variables to eliminate. And we'll see examples where they don't eliminate right away by adding. We'll have to do something else. But this one does right away. And so I get 5x equals 7 plus 3 is 10. And I continue solving for x, so I divide by 5. And that gives me x equals 2. So what I just did was I found the x coordinate of my parentheses, 2 comma something, where these two lines will cross. Because remember, if I wanted to, I could solve this by graphing. I could graph these two lines here because these are two separate lines, line 1, line 2. What we're noticing is they're going to cross somewhere at 2 something. Well, now we've got to figure out what that something is by taking the 2 that we just got and plugging it into one of the two equations. It doesn't matter which one. I'm going to choose the second one just because I don't have to do anything to the 2 when I plug it in for x. So it's just, if I erase, you'll see this is just going to be a 2 right here, so it's 2 plus 2y equals 3, and I'm trying to figure out what the y value is, so I need to get y alone or solve for y. So I subtract 2 from both sides, and I get 2y equals 1. And then I finish solving by dividing by 2, and I get y equals 1/2. So the solution is 2 comma 1/2. Okay? So that is where these, if I graph these two lines, that's where they would cross, at this coordinate right here, which is the solution to this system. Okay. Now, we're going to learn another method called solving by substitution. But what we're going to do is see problems set up like this one that look like we should solve them exactly how we solved the last one, by elimination. So when you see directions that look like this that says solve by substitution, don't do it by substitution. Do it by elimination. Why do a harder method? Solving by substitution is a longer method if it's not set up for it. This one is not set up for it because it looks like it's ready to do elimination. And the reason I know that is because it looks like I'm ready to add these vertically. The only problem when I add these vertically is that if I added them right now, I get 6x and then I get 2y's. One of my variables didn't cancel. We need one of the variables to cancel, to eliminate. So again, I'm not solving by substitution, I'm actually doing elimination here, and this is what I recommend you doing in the directions whenever they say solve by substitution, because no one's looking over your shoulder saying, oh, you didn't do substitution. We should do elimination if we want to, because it's a better method. So what we want to do here is notice the bottom. If I was to multiply all these numbers by 3, then I'd end up with a 3 right here, and my y's would cancel, and that's what I'm looking for. Okay, so what we need to do is, sometimes we have to multiply the top equation or the bottom equation by a number so that we can get a common number but opposite on one of my variables. Okay, so I'm looking at multiplying by 3 here, and that'll rewrite this to be the first equation, still the same, 4x plus 3y equals 4, and then on the bottom I get 6x minus 3y equals 21. Now I'm ready to add vertically and have variables cancel. My y's cancel. And then I get 10x equals 25. Okay? And now I divide by 10, and I get x equals 2.5. Now to finish, all I have to do is take my 2.5 and substitute back in for one of the previous x's here or in the top one. I'm going to put it on the bottom one though because it's a little bit easier. 2 times 2.5 is 5, so it's really 5, and then this was minus y equals 7. So that means I'm just going to subtract the 5, and I get negative y equals 2, which means that y equals positive 2. Okay, so that means my coordinate where these two graphs, these two lines would cross, would be at the coordinate 2.5, comma 2. Okay? So the way that works, again, whenever it says substitution and it looks like the same thing I did here for elimination, just do elimination again. But there are some examples like this one where you actually will want to do substitution. And when that happens is when one variable is already solved for. Like this one here, x is already alone. So when you see x is alone already, just go ahead and take that x. It's like they gave you an answer already. So all you have to do is take this 12 and say, alright, well that's part of my solution. X is 12, comma, I don't know what the y value is. So now all I have to do is find y by plugging the 12 in for x in the other equation. So all I have to do is write 2 times 12 minus 3y equals 6. And then just work it out and solve for y. So I go ahead and get my 24 minus 3y equals 6. And then continue solving by subtracting by 24. And I get negative 3y equals negative 18. And then just divide by your 3, negative 3. And you should get y equals positive 6. So your solution is 12, 6. Now sometimes when we want to solve by elimination, we have to multiply a number to the top equation and to the bottom equation, like this example here. Notice how everything's positive. The x's are positive, the y's are positive. So there's not any one single number that I'll be able to multiply the top by or the whole bottom by to make one of the variables cancel. So when that happens, you have to do kind of a least common multiple, an LCM. Okay? Least common multiple. And since so far we've been getting the y's to cancel, let's get the x's to cancel this time. So I need the x's to be the same number but opposite. So least common multiple of 3 and 5. Well, the only way to get that is to multiply them, and that's 15. Okay? So one of them needs to be a positive 15, other one needs to be a bottom. So since the bottom so far has been the negative, let's make the top one negative. So I'll multiply the top equation by a negative 5. The bottom equation I'll multiply by a positive 3. So if I distribute the negative 5 on top to all three of these, I would get negative 15x minus 35y equals negative 75. And then on bottom I'm going to distribute my 3 to all three numbers, and I get positive 15x plus 6y equals negative 12. Okay? And so then we go ahead and do our vertical addition like we were doing before, and the x's cancel, they eliminate. And then I go ahead and add my negative 35 and my 6 to get negative 29y equals 87 negative. And then to finish, you just divide by your negative 29. And it just so happens that 29 goes into 87 3 times, so it's y equals positive 3. Okay? So a little more work this time, but once you get it set up for one of the variables to eliminate, it still works out just the same as before. Still got a variable, y equals 3, so now in my solution I'm ready to have 3 and then just whatever the x value is. Okay? So I need to take this y value and plug it in either bottom equation or the top equation. It doesn't matter which one. Okay? So let's go ahead and plug it into the top equation. I got 3x plus 7 times 3 equals 15. Okay? So I get my 7 times 3, which gives me 21. And I'm going to subtract 21 to the other side, which means I get 3x equals negative 6. And then I just divide by 3, and I'll get x equals negative 2, which means my final answer is negative 2, 3. Now for my last example in this section is sometimes we have special cases. Okay, so I'm going to solve by elimination, and what you'll notice is the x's cancel, the y's cancel, and the number on the other side cancel. Well, that's really interesting and maybe confusing. Well, what we need to understand is that when something cancels, it actually turned into a 0, because I'm adding here, right? So 2 plus negative 2 is actually 0. Y plus negative y is another 0, so it's 0 plus 0 equals 3 minus 3 is 0. So what you actually end up with is 0 equals 0. Okay? Now, most of us are going to run and say, oh, the x's and the y's cancel, no solution. Well, actually, it's not. Because what you want to look at the end here is this a truer statement? So basically, is it true or is it false? Well, last time I checked, 0 is 0. So what that means is this is a true statement. So the question is 0 always equal to 0? Like always, forever, to maybe infinity? Yes, to infinity, it's always true. So what that means is this is infinite solutions. Okay, another way of saying that is all real numbers. I'm not sure what the lab says, but there's those options. You can say infinite solutions or all real numbers, basically saying the same thing. Now the last problem here at the bottom, let me put my bar at the bottom here. You've got to vertically add again, and then they cancel, and I get 0 plus 0 equals, and then these ones don't actually cancel on the right hand side. You end up with 12. So what we end up with is 0 equals 12. Now this time you need to actually think, again, true or false. Okay, is 0 equal to 12? And of course it's not. 0 is not 12. So this one's false. Since it's false, you got to think through, is it ever true that 0 is 12? No, it's never true. So what this means is it's never ever possibly true, so there's no solution. Biggest mistake I'm going to have is people get all the variables cancel, and then they'll take their 0 equals 0 and they'll say that it's no solution. Usually my students look at this and they understand that there's no solution, but it's usually trying to get us to not jump to no solution and actually think through infinite. Okay, so that's everything for this section.